Hi, I'm James Verdier, and welcome to the American Institute of Biological Sciences BioScience Talks, which is a forum for integrating the life sciences. On the second Wednesday of each month, and often in between, we discuss the latest bioscience publications. And as a reminder, if you'd like to read more, point your browser to academic.oup.com/bioscience. For today's episode, I'm joined by Dr. Joy Winbourne, who's a postdoc fellow in Lucy Hutera's research group at Boston University. She was here to talk about tree transpiration and its relationship with urban temperatures, which is something that's probably on a lot of our minds right now because of the current weather, at least in the US. Let's go straight to the interview. Dr. Winbourne, thank you very much for joining me today.
Yeah, thank you for inviting me. I'm excited to be here today.
Okay, so I think a lot of our listeners are going to be familiar with the urban heat island effect, at least in some sense, and probably in the sense that it's often a lot hotter in urban city centers than it is out in the suburbs or rural surrounds. What causes that effect? Can you tell us a little bit about that?
Yeah, the urban heat island effect, just as you mentioned, is, hotter temperatures in the urban core relative to rural areas outside. And there's a number of factors that feed into that phenomena. And one of them is that in cities, you have a lot more pavement than green space. And that pavement holds on to heat and re-radiates it, especially at night. So you tend to have warmer temperatures at night, especially due to the urban heat island effect. But also there's a number of waste energy, heat energy from buildings and things like running our ACs this time of the year in the summer that contribute to that hotter urban core.
And from the ACs, it's essentially the effect of the air conditioning is blowing hot air out and to create cooler air inside.
Exactly. Yeah. And that's especially happening as, you have these feedbacks that happen when hot temperatures, you get increasingly hot temperatures because we become more dependent on our ACs as extreme heat events happen.
Yeah. And that seems like the kind of thing that might be expected to worsen as it gets warmer in general.
Exactly. And so the urban heat island effect is happening in addition in synergy with climate change that's warming temperatures around the globe in different areas. And so we're expecting with climate change that there's going to be more magnitude and frequency of extreme heat events in cities.
Okay, so let's talk about trees a little bit and urban trees in particular. What kind of effects do they have on, the urban heat island effect and city temperatures in general?
Yeah, so trees are a great way to help cool the environment, especially in cities. And they're being proposed often in climate action plans that are happening throughout the globe to help mitigate and adapt to climate change and extreme temperatures, because they can help cool the environment in a number of ways. And they can cool the environment through shade, which anybody walking down a nice canopy-lined street in the city on a hot day knows that it's much cooler because they absorb and prevent the radiation from reaching the pavement below often. But another way, one that we really focused on and dug into in this manuscript, is that they can cool the environment through transpiration. And so you can kind of think of that as if you've been at a restaurant where they have like misters out on really hot days, they're misting you with water. That water is evaporating and it's going from us. And the transition from a liquid to gas phase helps to cool the local air temperatures around you. And so trees do that through transpiration.
Okay, would it be fair to think of that in terms of, as if the trees were sweating, say?
Exactly, yeah. So that's actually one of my favorite ways to kind of explain it is the trees sweating. And in some cases, they really are sweating. So the reason it's happening, transpiration, is because trees are able to pull water up through their roots, through their stems, to their leaves. And it's happening because they're doing photosynthesis. They're fixing carbon, opening their stomates, which I like to think of as their little mouths. They open their stomates to bring CO2 in, and as a consequence, they lose water and it evaporates.
Does that serve the purpose for the tree of cooling it? Or is this mainly just an effect that we benefit from as city dwellers when we're surrounded by trees?
A little bit of both. So it is definitely an effect of them photosynthesizing and them losing water because they want to keep their stems from cavitating and dying. But there is evidence showing in really extreme heat events that trees will stop photosynthesizing but still transpire water. And we think that's because they're trying to cool down their leaf temperatures.
Okay, and so, how has this information been applied thus far in terms of city planning? Obviously there are trees in cities. But what have been the main focuses and aims, and has it been effective?
Yeah, trees are, as I mentioned, being proposed as a solution to help mitigate and adapt to climate change. And they serve a number of other co-benefits and disservices too. There's some aspects of trees that people don't love about in cities when they like dig into your pipes, your sewer pipes looking for water, for example, or branches fall on your car. But also they can produce VOCs, volatile organic compounds, which can have effects on air pollution. So trees can they have a number of services and disservices to consider with urban planning. But from the perspective of how they influence urban temperatures, most of the work has been focused on kind of how they affect shading. So thinking about what trees to plant, where, and what sort of characteristics, morphology of the trees that will influence their cooling effects. And we really dug in this manuscript trying to better understand the other aspect of how they cool the environment, transpiration, what things we need to better understand, what we do understand, and how that could influence tree selection and planning of where to plant trees.
Okay, discussing transpiration specifically, how is that measured in this kind of environment? What does the experimentation look like? And how do you extrapolate those results to, citywide scales and those sorts of things?
Yeah, great question. So outside of cities, you can use tower-based approaches, which allow you to put instrumentation on top of a tower and for a large area, understand what the rates of transpiration are. But in cities, we can't really get away with doing that because the landscape is so heterogeneous. There's, patches of green space or street trees and buildings of different sorts. And so you need to use ground-based approaches. And so the way to do that is use these sensors called sapflow sensors, which are really cool. You put inside the trunk of a tree, and they use heat typically as a tracer to measure how fast water is moving in the stem of a tree. And because transpiration and photosynthesis are so tightly coupled, we can then understand how much water is coming out through their leaves and measure total water usage. So we use sapflow sensors, these ground-based approaches to quantify transpiration at the tree level. It integrates across the entire tree's activity, and we can extrapolate that to urban areas using models, so urban climate models, which allows us to translate the cooling effect that transpiration can have to urban temperatures by incorporating many of the other features going on in the urban landscape.
So I'm curious now, what is the effect actually, like in terms of having trees? What sort of temperature benefits are you receiving as a service? When you have a tree-laden area in an urban setting?
Yeah, so studies have found that trees can have pretty significant effect on the temperature. So it can range from cooling the local environment around the tree from 1 to 8 degrees Celsius, but also upwards of 20 degrees Celsius for the surface temperatures. So they can have pretty significant effects, and that effect is intertwining both their effect of shading and transpiration. And without these sort of sapflow sensors that I mentioned, these sort of ground-based methods, we can't really disentangle the effect of shading from transpiration.
Okay, and so I'm wondering also, are there trade-offs in this? Because obviously, if the trees are taking up water and transpiring, that water has to be coming from somewhere. Is it typically found, just from rainfall in the cities, or do you require sort of irrigation efforts and that kind of thing?
Yeah, so there's big time trade-offs, especially depending on where you are, what city you're in. So a lot of work has been done in kind of the LA area, looking at water use by trees and finding that it's a big time trade-off. It's up to 50% of the residential water supply that's going towards irrigating trees. Because in arid cities, trees don't grow there naturally. We have to irrigate them. And even in mesic cities, so cities like Boston, where we were doing a lot of our research, we have more rainfall, but still during dry periods, we don't want our trees to die, so we irrigate them quite a bit. But for trees that aren't irrigated, and even for trees that are irrigated, we find that they access other water resources, groundwater. They are known to dig their roots into sewer pipes. So there's a number of water resources throughout the city, and that really affects the rates of transpiration that we're going to observe. And it's a bit of an unknown too. We don't entirely understand where trees in the city get their water from.
Oh, that's interesting. So it's a combination of factors. Then it's a little bit uncertain, but obviously in some areas you have a need to irrigate, and in others at other times they can be left to more or less fend for themselves.
Yeah. And that has a big impact on how much transpiration. That's one of the driving factors of kind of the cooling effect that trees can have from transpiration, is where they access water. So, for example, we installed these sapflow sensors in trees growing inside cities and outside of cities in the Boston area to kind of understand the influence of urban environment on tree transpiration, because it's both water access. So we looked at a tree that was being well irrigated, but in cities you also have warmer temperatures. We might have more nutrient availability from fertilization. And also less competition. So there's a number of factors in cities that promote more growth and transpiration of trees. But there's also a number of factors that can negatively affect tree growth. So trees they're warmer, as we mentioned, which can create heat stress if it's too hot. And if trees can't access water, especially young trees have difficulty because they don't have a well-established root system. Those can have negative effects. And the addition in cities like Boston, we put a lot of salt on the ground. So different contaminants can really affect tree growth and therefore how they can influence the environment around them.
And the salt being there because you have rather cold winters in contrast to the warm summers, and you need to melt snow.
Yeah, exactly.
Okay, so what kinds of things do you find looking at trees in the urban environment, versus other settings? Were there any major surprises?
Yeah, one of the major surprises, mentioning our study looking at transpiration rates in urban trees, is we looked at its relationship of how much it was transpiring with temperature. And our models predict that there's kind of an optimal temperature that plants photosynthesize at, and we would expect that to be a little bit higher in urban areas. But after you reach a certain threshold where it's too hot for the trees, they're going to lose a lot of water and potentially injure themselves, so they close their stomates and stop photosynthesizing, stop transpiring water. But what we found, looking at our sugar maple in Boston compared to rural sugar maples growing outside of Boston, is that the urban ones keep transpiring water at very hot temperatures. And we think that's because they are being irrigated. And so kind of our theory is that was very surprising, because it was counter to how we our theory and how we incorporate them into models.
And is that as a result of they have greater water availability, so they're not being stressed in that particular way, so they're more likely to continue transpiring?
Exactly. That's what we think is going on. And what would be really interesting to see is how this extends with really hot temperatures. And so digging into the literature, we found that there's only really one study that's been able to manipulate extremely hot temperatures. They did this in Australia. And so they had temperatures of 43 degrees Celsius, and they did this in a heat wave kind of simulation, because plants we know are adapting to hotter temperatures over time, but how do these sort of pulses of extreme heat affect their behavior? And they found that they sweat. They stopped photosynthesizing because the machinery of photosynthesis doesn't do so well at 43 degrees Celsius, but they continue to transpire and do so by tapping water resources deep in the ground.
Okay, that's interesting. Now, I'm also wondering about, the potential variation with tree species. Are these results generalizable across a number of species, or is this something that you only would expect in, with certain types of trees?
Yeah, that's a good question, and a bit of an unknown. So we know that trees vary quite a bit in their hydraulic strategies, so their strategies in regards to water use. So there's variation in how efficient different tree species are in their use of water. And they also vary in their wood anatomy. So how they kind of move water through their stem can really affect their water movement and then transpiration rates. So it's still a big area of research that we kind of highlighted as kind of future research directions that need to be taken, is to kind of understand kind of functional groups of trees that behave differently.
And obviously that would have I would imagine at least a larger effect than you might, have in other, types of considerations, because you actually get to pick the trees that you're going to plant in an urban environment to some extent, which you wouldn't necessarily have to the same extent in a, say a national forest or something like that.
Yeah, exactly. So you can really, and that's part of better understanding how these different tree species vary in their response to urban environment can help us better select trees. And that's an interesting point too, is urban areas are really unique in that we plant trees. And so we have tree species that don't have any non-urban counterpart, especially in cities like LA or very arid areas. A lot of tropical species are brought in to live there. And so we don't know how they're going to behave. Is it going to be the same as kind of their native habitat or non-urban areas? And that's the thing. And broadly, a lot of the research has kind of assumed that urban trees will behave like rural trees. It's just the environment is different. But the comparison of kind of urban trees to rural trees, I think, is a really interesting one, and one that the research group I'm in has done quite a bit of work on. And we found, for example, in the Boston area, that street trees in Boston grow 4 times faster than their urban counterparts outside of the city.
That's incredible. What accounts for that change? Is it just the greater water availability, lack of competition? That seems pretty dramatic.
Yeah, exactly. And that's a great question. The mechanisms behind that are still a little bit unknown. We have a lot of hypotheses because of these sort of beneficial conditions that urban areas can have. But we think the reason is they don't have competition. Typically, urban trees are open light conditions. So they have more light, potentially more nutrients, not just from fertilization, but cars produce a lot of nitrogen deposition, and other sources of nitrogen deposition in the city can have beneficial effects on tree growth and access to water, that we either irrigate them, or in kind of more mesic cities like Boston, they can access groundwater.
Okay, and it may be too early to answer this question, but I'm wondering if there are any takeaways from your work thus far, either in the article or not yet, about what city managers should be thinking about doing in terms of planting trees. Of course, you mentioned the adage that it's always the best time to plant a tree is 20 years ago. But is there any specific guidance that's coming out of the work on transpiration that might, guide some decision making? Obviously, we're not making policy recommendations right here, but what sorts of things should they be thinking about, those who manage cities?
Yeah, I think the body of literature really on this, studying trees and the benefits they can have, has shown that protecting your old trees is really important. Kind of like that proverb says, like, the best time to plant a tree was 20 years ago. Our big trees are the ones that transpire a lot more. They fix a lot more carbon. They're bigger and therefore have bigger benefits on the urban environment. And they're able to withstand the stresses we find versus small trees. So small trees are more likely to die, have high mortality early in the first couple of years after they're planted. And so to answer your question, I think what's coming out of a lot of work is showing that we need to protect our big trees. They often get cut down during different developments and replaced with lots of little kind of twigs in the ground. So I think that's one thing that's coming out of this. And second, if we can't, we're trying to plant more small trees to really protect them in the early stages of growth is being found to be very important.
Is that because they're vulnerable in those early stages?
Yeah, they're vulnerable because they don't have the same sort of root system. They're smaller. They're more susceptible to a lot of the stresses that their environment has that larger trees can withstand.
Okay, and what's coming next for your work? What sorts of things are you looking at in the future?
Yeah, so I've been really interested in this question of how trees in urban environments respond to extreme heat events. And so some of the work we're doing right now is in Boston. We're instrumenting a number of different trees that grow in different urban environments. So we kind of mention in the manuscript quite a bit that understanding urban transpiration means understanding different places where trees are growing. How does, like, a forest patch versus a street tree that's irrigated versus not, how they respond to the unique conditions that they're in. And so we've been working in Boston, putting out sapflow sensors on different tree species that are growing in different areas to get a better understanding.
And are there any early hypotheses on, kind of how those things will work? Are there big differences between a stand of trees that are, in a place like, for instance, Central Park, or, versus lining a street that's otherwise, populated by tall buildings?
Yeah, so the research is still new. COVID kind of prevented us from doing some early season deployments. But our hypothesis is that a large forest stand obviously is going to, when you scale it up, it's going to have higher transpiration, but also trees that are found in well-irrigated landscapes are going to continue to transpire, especially during heat waves, while non-irrigated trees will not transpire as much, especially at those hot temperatures. And understanding those hot temperature responses has really important implications, because you can have these sort of negative or positive feedbacks that happen. So if a tree continues to transpire during a really hot event, then it's cooling the environment, and that could reduce our need for use of ACs, which have that sort of excess heat that they produce when they're being used. And so, and if trees don't continue to transpire during heat events, it can kind of create a positive feedback loop of hotter temperatures, more dependence on air conditioning units, more excess heat being pumped into the area.
So that could help guide policies and practices that attempted at least to avoid that kind of scenario in which you're doing everything you can to make it warm or cooler inside, and as a result you're making it even hotter outside.
Yeah, and I think to answer your question on future research directions, another one is to better understand these sort of overlaps between canopy and the built environment, that interaction that's happening between the trees that are there and the energy use that we have. And some of that work is being done by my colleagues. Dan Lee, who's a co-author on this paper, is an urban climate modeler. And so that's really how we can translate these sort of ground-based observations to how it's affecting the kind of larger scale.
Okay, and I guess, to close out, one thing I was curious about, and I've been asking everybody, and you've mentioned already, in fact, is, what sort of effect has the COVID pandemic had on your work? Has any of it been able to be carried on, during this spring, or have you had to put everything on hold and are, kind of awaiting opening up of things again?
A little bit of both. It's definitely affected, kind of, especially because of the timing. It was March, the start of the growing season here
Right.
in Massachusetts. It definitely put a little bit of a halt on things, a little delay. But you got to get creative. So one of our colleagues kind of turned his backyard into a field site so that we could continue to work on this sapflow sensor, which is a newly invented sapflow sensor. So we've been making lots of very innovative changes to kind of how sapflow is measured, to create these sort of sensors that you can deploy large networks of, and in cities where they can get easily vandalized. So it's powered off of battery, USB battery, so you can kind of tuck it up on the trunk, and it is much more compact than other ways, which is part of why we, in our synthesis, what kind of led to this is in 2010, there was 5 studies done in cities looking at sapflow. And now we found 40, which is a lot more, but still very little research done in cities kind of understanding transpiration at the ground level, at the tree level. And part of this is methodology. It's a lot of sapflow sensors they need line power. So it makes it difficult to deploy them.
Yeah, and I guess that's another question I should have asked earlier about the sapflow sensors. So you're able to run these off of USB-powered battery packs?
Yeah, our latest version is off of that versus kind of heavy lead-acid batteries. But yeah, we use a sapflow sensor that kind of uses heat as a tracer, but it pulses the heat, so it's not continuous, so it doesn't use as much energy.
Oh, that's interesting. And how far up the tree is it, or does it have to be?
Yeah, we put it up kind of high, so people can't reach it and mess around with it.
I was thinking, yeah.
Or try and, yeah. But actually, people have been pretty great in Boston and haven't been messing around with them. So you put them up high on the trunk, though. Not too high, but on the stem, the top part of the stem. A lot of sensors are put in like parks or on campuses because it's less vandal, like you can better watch it, you can have access to ground power. So kind of innovating these sensors so that they're small, compact, and powered off of something small and compact that you can stick up high in a tree makes it so that we can measure these things in areas that were more difficult to do otherwise.
Oh, that's fascinating. So before, would you have a problem in which, you were sort of like the person who lost his keys and was only looking under the streetlight, because that's where the light was?
Yeah, exactly.
Would you sometimes have the same issue in which, you're applying sensors to trees, but you're only applying it to the trees that are most easily censored?
Yeah, most easily next to line power. So a lot of the studies, as I mentioned, there was 40 studies that I found in urban areas that use sapflow sensors to look at transpiration. So these kind of ground-based approaches. And the majority of them were done in parks, kind of close to campuses and stuff like that. I think because of the easeability and also permission. So in urban landscapes, you have to get permission to install sensors on people's properties or from the city. So I think that's also part of it.
Well, that's fascinating. And Dr. Winbourne, thank you very much for joining me today.
Yeah, thank you for having me. It's been really fun.
And that concludes this episode of BioScience Talks. Just a reminder, the journal BioScience is published by Oxford University Press on behalf of the American Institute of Biological Sciences and is made possible by the support of our members and donors. Thank you, and talk to you next time.